Hello, welcome to this is the 24th class in our series of lectures on physics of materials. So, in the last class we have looked at what we can expect when we have an electron that is bound in some manner, in fact in the form of a potential well, and the fact that in a material there are a couple of different levels at which a couple of different extents to which an electron can be bound. It can be bound within a potential well that is very narrow, that and therefore then it would be called a bound electron, or it could be a nearly free electron, in which case it is free to run through the extent of that solid. Okay. So, just to reiterate what we did, we had a potential well, we can make a minor modification. We can say that the entire dimension is a. We even did from minus a to plus a, but let us say this is 0 and this is a. Okay. So, we basically had when we solved the Schrodinger wave equation, which was we recognize that in this problem we are saying that the potential is 0 within this well, and then it is infinite on either side of the well, therefore the electron cannot come out. So, since this is 0, this term reduces to 0. So, we simply had d square xi of x by dx square, I am sorry, this is dx square equals minus 2 me by h bar square xi of x, and therefore we recognize that a typical sine or a cos function would satisfy this equation, because the second derivative of it would be a constant times the same function, a negative constant times the same function. So, we wrote it as a possible solution as a cos kx plus b sin kx as the form of the xi of x, okay, or rather xi of x is this, and we do not know what a is, what b is, and what k is, and so on. So, we find that if you differentiate this twice, you will find that d square xi by dx square equals minus k square of xi of x, essentially a cos kx plus b sin kx, right. So, therefore k equals this term here, okay, or k square equals that term, k square equals 2 me by h bar square, or we can also say implies E equals h bar square k square by 2m, simply taking this equation here and rearranging the terms we get that equation there, okay. And we also said that in our particular problem we used minus a to a, but we can also do the 0 to a. At 0 the wave function has to drop to 0, because the probability of existence of the electron is because this is an infinite potential past this point, the probability of its existence past this point is 0, and it has to sort of stay, we assume that the functions are well behaved, therefore it has to drop to 0 at that point, so that it can remain 0 past that point. It should not be at some value and then abruptly drop to 0, we assume that of that function. So, it drops to 0 at that point and then remains 0 past that point. So, it has to drop to 0 here plus drop to 0 here, okay. Only then that xi star dx, the probability of finding the electron at a location x to x plus dx, which we said was the Born interpretation of what the wave function was, only then that probability of finding the electron will drop to 0 past this point and past that point, and therefore it has to drop to 0 at that point, okay. So, therefore we have if you look at 0, when you put x is equal to 0 in this equation, and you say that xi of x should become 0 at xi of 0. So, xi of 0, xi of x at x equal to 0 is simply xi of 0, cos of 0 is 1, okay. So, it will become a, and sine of 0 is 0, therefore this term will reduce to 0, therefore we will simply have xi of 0 is simply a, and that has to be equal to 0, therefore a is equal to 0, fine. So, therefore this term is no longer valid in this equation, I mean not valid in the sense it reduces to 0. Then we also have xi of a should also equal 0. What is xi of a? We already see that the first term is 0, so we can neglect this first term. So we have b sin ka should be equal to 0, implies b sin ka should equal 0. For this to happen, regardless of the value of b, we are saying that a trivial solution is b is 0, but non-trivial solution is that ka should equal n pi. Okay, or whenever it is n pi here, sin of n pi is 0, where n is an integer. Therefore, or in other words, k is only allowed the values n pi by a. So this is the result we got yesterday. We got it a couple of different ways. We looked at a string, we also looked at the Schrodinger wave equation. Again, this is still the Schrodinger wave equation approach. I have used 0 to a, and I also said that the extent of this what shall I say, the extent of the well, for the material we have we found that there are two different levels of confinement. One is the length of the material, the other is the ionic core itself, the dimension of the ionic core. So in one case the electrons that are bound by the ionic core, this a works out to be in the level of angstroms, and for the electrons that are nearly free, this a works out to be the value of the length of the material, right. So this is so this k can have significantly different meanings, and we saw that when you plot this function here, for a free electron all values of k are allowed, therefore all values of E are allowed. For a bound electron in any form, only specific values of k are allowed, and therefore only specific values of E are allowed. Now the closer spaced the k values are, the closer spaced the E values are, and the larger the value of the denominator, the more closely spaced those k values are, okay, because they are tiny values. The next value would be a very marginal difference from this value, okay. So therefore for the nearly free electrons, okay, so when we write this, when you draw this, I will just draw one potential well here just to illustrate the point. For the nearly free electrons which fill this place here, we also indicated this is E phi, Ef, Fermi energy, and this is the work function phi. This is potential in that direction, and this is distance or location, distance. So here even though I mean for our visual purposes I have drawn it like this, there is a world of a difference in the dimension of this versus the dimension of this. This is of the order of angstroms, this is of the order of meters, right. Therefore here the k values are n pi by L, and here the k values are n pi by a of the order of angstroms, L of the order of meters. Okay, 10 power minus 10 meters. So what we find is because this is a very small value here, it dominates this term, and therefore for every value of n the spacings are different. The allowed energy levels, which are all E equals h bar square k square by 2m, these values are very widely spaced for electrons that are bound within this narrow region, okay. So they are very widely spaced. So you will see one energy level here, allowed energy level, next allowed energy level will be somewhere there, and so on, okay. So these are the exact locations you will have to do the calculation to see, but the point is they are very widely spaced relatively speaking in energy, okay, and this spacing could be of the order of several tens of electron volts, okay. So I will put those numbers down, several tens of electron volts or even 100 electron volts between these values of energy levels that are present in the bound electrons. Here on the other hand they are still discrete, it is not a continuous spectrum because only specific values of k are allowed, okay, not all values of k are allowed, but they are much closer. Okay, so they are very close. In fact, drawn to this scale you would not even be able to distinguish between them, they are that close, okay. That is the reason why, I mean of course later we will relate this to bands and all that, but just for a very loose connection if we want to make at this point, when we look at a band, when you say conduction band, valence band, at first glance it appears that entire band consists of allowed energy values. Actually even within them there is a very fine detail is there of what is the allowed energy value and what is the not allowed energy value. That detail comes from this level of spacing between to some degree is commensurate with this level of spacing. So here the spacing between these allowed values is of the order of 10 power minus 10 electron volts. Okay, so 10 power minus 10 electron volts is the kind of spacing that you see there, and the kind of spacing that you see here is of the order of several electron volts to tens of electron volts. Okay, so several electron volts to several tens of electron volts or even 100 electron volts of that order. So it is a huge difference between this and the spacing there. And when you talk of just to give you an idea of scale, when we talk of band gap, which we have not come anywhere close to that concept yet, we are not really talking of that yet. Just to look at comparative values, band gaps are of the order of electron volts, 2 electron volts, 3 electron volts, 4 electron volts, that is the kind of value we are looking at, 1 electron volt. Okay, so of the order of an electron volt is a band gap. Of the order of 10 power minus 10 electron volts is the spacing between these energy levels, and the spacing between these energy levels is several tens of electron volts if not more. Okay, so that is the so that is just I have put this down so that you get a sense of how, of course, how we have gotten here, how we are understanding now that confinement of electrons leads to quantization, and what quantization of energy values. Okay, so confinement of electrons leads to quantization of the energy values that are allowed for those electrons, that now they cannot any longer accept or assume any energy level that they wish. Okay, but the general form of the energy versus wave length that or wave vector that is there is still the same. It is just that only specific values of k are allowed, therefore only specific values of E are allowed. So that is the thing. So and so when we make a plot, instead of having a continuous plot, there are only specific points along the plot that are the actual allowed values. The rest of in between those points there are values which are not allowed. Okay, so that is the picture. Fine. Later we will use this picture, and I just want to perhaps just highlight one point again, simply because these energy values are very large. Okay, spacing here is large, spacing here is very small. If you draw that to this scale, you will almost see a continuous energy value. It will look like that. Okay, so that is a concept that I want you to keep in mind. We will later use it when we a couple of classes down the road or few classes down the road we will use it. At that time I will alert you to it once again, but to this scale it will look almost continuous. Okay, so but actually they are all discrete, all these energy values now are discrete. Fine. So this is the picture. Now we write E equals h bar square k square by 2m, but we also recognize that k is n pi by a, right. So we can actually put this value of n pi by a here. So we can also write E equals h bar square n square pi square by 2 ma, right, or we can put it as equals h bar square pi square n square by 2 ma. Fine. So energy versus k relationship is there, and we have now converted that to energy versus n relationship. In the language of physics, okay, so when we look at these kinds of topics and we address them in using the language of physics, what the way in which these things are described is as follows. When you draw something in using the using axis corresponding to a particular quantity, we say that we are discussing the topic in that space. Okay, so that is the kind of language that is used. So for example, this is a vector k vector. Okay, I have done a one dimensional case, that is why we simply have k. In principle we could have kx, ky, kz. Okay, so that is how we could have. So we can discuss this entire conversation as though we are plotting everything in the coordinate axis of kx, ky and kz, and this in all the energy information corresponding to the system can be plotted in that axis, because the equation is there. Anything you can plot using energy you can convert and plot using k, because they are related to each other, right. So you can actually plot them in kx, ky, kz axis using those as the axis. When you do that, we say that we are representing the information in k space. That is the way the description is used, okay, made. We describe it by saying we are representing the information in k space, that is the description. So whenever we say we are in k space, this is simply all it means. It may seem very complicated, it may seem like we are talking of something very fancy. In some sense it is not, because it is a very straightforward relationship. As long as you know the relationship, you can always plot it in, if you know the relationship between two quantities, you can plot the information in terms of one quantity or in terms of the other quantity, it does not matter, because you know the relationship. But because of the relationship, the picture may look different. The final plot that you see may have a certain shape if you plot it using one variable, it may have a certain different shape if you have plotted using the other variable, simply because of the way in which they are related. But the information that you get out of the two should be the same, because they are the same, this exact relationship has been used, that is why the information you get should be the same. It turns out that in some cases one set of axes is more convenient to use because of the manner in which that variable is behaving, and therefore we will switch from one space to another space as necessary whenever it is convenient. So when you plot using k, it is called k space. Similarly you can plot using n. In this case n is a quantum number here, okay, because it is in steps of n that the system is changing, right. So you have I mean n can take values 1, 2, 3, 4 and so on, so there that is quantum number. So this is actually quantum number space if you plot it versus n, okay. So this is k space, this is quantum number space, so that is how it is. And again this is also done only in a one dimensional sense right now. Strictly in 3 dimensions, n square equals nx square plus ny square plus nz square. So in 3 dimensions this is how it will be, right. So if you want to write it again in 3 dimensions, this is the same as saying E equals h bar square pi square by 2 ma, right. Times nx square plus ny square plus nz square, pi square k square. I am sorry, this is 2 ma square here, okay. So this is a square here, because it is n square pi square by a square, n square pi square by a square and n square. So k equals n pi by a, so k square we have plotted, so it is n square pi square by a square, so that is what we have. Now the point we have to once we put down this relationship, the point I wish to I want to draw your attention to is that the way E is related to n is such that all values of n, this combination of nx, ny and nz that result in the same amount of energy, okay, all values of n that result in the same amount of energy will lie on the surface of a sphere, okay. In other words, when energy is a constant, okay, when any given value of energy we take, let us say that one constant value of energy we take, it means that nx square plus ny square plus nz square has to be a constant, right. That is the equation of a sphere, a spherical, it simply means any vector, see if you have a vector n which consists of which the where its components along the x, y and z direction are nx, ny and nz, the modulus of n is simply nx square plus ny square plus nz square, right. And as long as the modulus is the same, if you keep changing this but the modulus works out to be the same, you get the same value of energy. What happens when you change nx, ny and nz such that the modulus remains the same? You are actually tracing a sphere, in all directions you are moving, but you are tracing a sphere, right. So you can look at it physically, you can look at it mathematically. Mathematically simply it means nx square plus ny square plus nz square is a constant, and if it is a constant we are talking of a sphere. So all values of all points in k space, all points in quantum number space which form a sphere represent the same energy, okay. So that is an important piece of information that we wish to have, okay. So this is some information we have, we will keep this here for the moment. From here we will do something slightly different, because we have actually come far enough that we can actually go back to one of the issues that we were trying to discuss earlier, but we said at that stage that we do not yet have all the information and all the tools in hand, so we need to develop certain things and then come back to that point, right. So we have developed certain things already, which is why we have this equation here. So we can now go back and actually look at a little more of a detail of something that we left open-ended at that point. And the detail was simply this: I basically put the Fermi Dirac distribution f of E like this, right. This is energy and that is the probability of occupancy. Now when we discussed this, I told you that this picture is an incomplete picture because it is not really telling us how many states are actually available at each energy level. It simply says what is the probability of occupancy. Okay. So we will now define, so in other words, we may have only 5 states here, we may have 500 states here. So just looking at a square diagram like this, if you are not sure what you are talking of, you may get a misleading idea that the number of energy levels is the same at all, number of states available at every energy level is the same. That is not the case here, because this is not the number of energy levels, it simply is the probability that those levels are occupied. There may be 5 states here, it means all 5 states are occupied. There may be 50 states here, it means all 50 states are occupied. There may be 500 states here, it means all 500 states are occupied. That is the basic information that it is giving you. It is not telling you how many states are there. That is independently we have to find out. So independent of this picture, we have to find out how many energy states are available as a function of energy, and taken together you will get the full picture of the situation, which is how many occupied states are there in the system. So what we are really looking for is a parameter that we represent as d of E, okay, and d of E is called density of allowed states. Okay, effectively it is the number of states in the energy range E and E plus dE, E to E plus dE. Okay, so if you know the number of states in the energy range E to E plus dE, in that small dE between E and E plus dE, that is this density of allowed states, and if you define n of E as the density of occupied states, okay, so density of occupied state, then n of E is equal to 2 of f of E d of E, and I will just explain it. This 2 factor comes from the fact that if you say that you will if you have not accounted for spin, then in a given state you can have a spin up and a spin down, so you can have 2 electrons per state if you want, if that is the way you have done your calculation, that is why this factor of 2 comes. But if you set aside this 2, even if you do not bother much about this 2, the density of occupied states is simply the product of the density of allowed states times the probability that those states are occupied, that is all, right. That is quite straightforward. This is the density of occupied states, this is the density of allowed states. The fact that these are allowed does not mean they are necessarily occupied, they may be occupied, they may not be occupied. Whether or not they are occupied is decided based on the probability of occupancy. If it is 100%, then all of them are occupied, if it is 50%, then only 50% of them are occupied, right. So the density of occupied states is the density of allowed states times the probability of occupancy, and of course since it is a density, we are still talking of we are talking of this range E to E plus dE, fine. So this is what it is. So density of occupied states is the density of allowed states times the probability of occupancy. For us it is of interest to get a expression for this, we would like to get an expression for this. Okay, so what we will do is actually we will approach this problem from 2 different directions, and so we will have some 2 different expressions that we will have, and we will be able to relate those 2 expressions, and in the process we will get this d of E. Okay, so so we will do that. Okay, yeah. So now the first approach we will take is that we wrote this we noticed that basically all states of equal energy lie on the surface of a sphere in n space. Okay, so this is something that I just explained to you. If you write and so we have just discussed that. So you understand now that since it is simply E is equal to h bar square pi square n square by ma square 2 ma square. Okay, so simply because we have this situation, all the states of equal energy lie on the surface of a sphere in n space. Now we also want to we also wish to point out that n is an integer. Okay, so it means it can only take positive numbers, positive values. Okay, so n can only be plus 1 plus 2 plus 3 plus 4 and so on, and if you write it as nx ny nz, the values of nx ny and nz can also only be positive numbers. They can only be plus 1 plus 2 plus 2 plus 3 plus 1 plus 2 plus 3 like that. Okay, so they can only be positive numbers. So what we will do is we will look at the we will say we will see if we can look at what is the total number of allowed states okay, the total number of allowed states below an energy value E subscript n. Okay, so total number of allowed states up to an energy value of up to, we will say, below is the same as that, up to an energy value E subscript n. Up to an energy value of En is simply given by the volume of so you have so it is given by the volume of the sphere in n space divided by the volume of a single state. Okay, so I will write it down and then we will explain it, equals volume of sphere in n space okay, and that is quite straightforward. You have the number of states, each of which has some unit volume, and taken together they form a sphere. So you take the volume of the sphere, you divide by the volume of a single state, you get the number of states. So that is what it is, except that here it says volume of the sphere, but I just pointed out that we are only allowed positive values of nx, ny and nz. Therefore we do not take the entire sphere's volume, we take only the volume of the sphere in the first octant. If you look at a sphere and you divide it into x, y and z, so only 1/8 of the volume of a sphere you take. Okay, so the numerator is simply 1/8 4/3 pi n cube, that is the 1/8 of the volume of the sphere. 4/3 pi r cube is the volume of a sphere of radius r. It's a cube, I mean here the radius is being measured in terms of n, the quantum number, and so therefore this is the volume of that sphere, a generic sphere of radius n, but only 1/8 of the volume is in the positive quadrant, which would correspond to positive values of nx, ny and nz, which total up to this n. Okay, so that is what it is. Now in quantum number space, the volume of a single state, the step size is 1, right. So n can take values 1, 2, 3, 4 and so on. So the step size is 1, the step size in the ny in nx direction is 1, in ny direction is 1, in nz direction is 1. So the unit volume per state is 1, okay. So this is 1 divided by 1, and please note we are talking now of the number of allowed states. This is still not we have said nothing about occupancy at this stage. In this calculation, the way I am doing it right now, it is only the number of allowed states, nothing has been said about whether or not they are occupied, okay. So this is simply whatever the numerator is, 1 by 8, or okay, so this is we write it as 1 by 6 half, so 1 pi n cube, alright. So this is all it is. So we will take it from here. We wrote energy as h bar square pi square n square, we have written it there, by 2 m a square, okay. So we now have a relationship between energy, and we already have a relationship between energy and the quantum number. Now we have a relationship between the total number of allowed states up to upper limit of energy E n and the same quantum number, okay. So we have those two relationships. So if you use the previous relationship and substitute here, we will now have a relationship between the number of allowed states up to an energy value E n and the energy, because we have a relationship with the quantum number, and quantum number and energy relationship is there. So we will just substitute that. So n, which we will call as n of E n, number of allowed states, n cube we need. So here this implies n is 2 m a square E, okay, by h bar square pi square power half, right. Just rewriting this, this is the numerator becomes 2 m a square E by h bar square pi square, by h bar square pi square. So this comes down here, that is n power half, and we need n cube here, 1 by 6th pi n cube. So this simply will become 2 m a square by h bar square pi square power 3 by 2 e power 3 by 2, right. So this is what we will get, e power 3 by 2 is what you will get there, because all we have done is I have taken a cube of this, this is n, and this is n power half, so this is this term times half, and we want n cube here. So I have cubed this whole thing and brought e outside just because we are going to do something with it, so this term is still here, power 3 by 2 e power 3 by 2. So this is what is the total number of states up to an energy level E n. So now density of allowed states, so if you look at, if d of E is the density of allowed states, right, then this number, the total number of allowed states up to an energy level E n, is simply the integral of this with respect to energy, that is all it is, right. This is the number of allowed states between an energy value E and E plus dE. If you integrate that from 0 all the way up to an upper energy level of E n, you should get the total number of allowed states up to that energy level E n, that is all it is. So that is how these two relate to each other. So n of E n is simply integral 0 to this value E n d of E dE, okay. It is just based on definition, that is what it is. This defines what is the number of energy states between E and E plus dE. We want all the number of states, the total number of states between 0 and a higher value of E n. So you simply integrate this thing as from 0 to E n, you should get this value. Or if you reverse this, if you differentiate this with respect to E, you should get dE, that is all you have to get, right. So d n of E with respect to E equals d of E, fine. So now we already have an expression for E of n. If you differentiate this with respect to energy, you will get d of E, fine. So what we have done, we have approached this problem from two different ways. We have looked at the total number of states available in the system and treated that as, you know, 1/8 of the volume of the in n space, and then independently we have also looked at the energy associated with the system and how it relates to n. So we got an expression between energy and n, and since we have a relationship now between the number of states and the quantum number and energy and quantum number, we now have a relationship between the number of states and energy, okay, because the quantum number is common to both those relationships. And then given that you have a relationship between the number of allowed states and energy, we are able to get an expression for density of allowed states, which is simply the differential of this, okay. So if you differentiate this with respect to E, you will get d. So if you differentiate this expression with respect to E, you will get 3/2 will come here and it will become e power half, right. So this implies, so you just differentiate this expression with respect to E, so 3/2 will come here, so 3 will go, so this will become 1/4, so this has become pi by 4, okay, and this will remain the same. We will not disturb this in any way. Did I do it correctly? Yeah. So this is what we get. So this is d of E, and incidentally a square power 3/2 is a cube, and a cube is the volume of the system that we are talking of, okay. So if you want to write it as volume, we can write it as volume, but the main point we make here is that d of E as a function of E is actually parabolic, okay. So you see this E and d of E are related like this, fine. So now if given that we have this relationship, and we also know that we know the manner in which the Fermi-Dirac statistic function behaves, right. So we have so we now if you plot d of E, okay. So if you plot d of E versus E, so you will get a function that the basic behavior will look like this. So this is the density of occupied states as a function of energy, right. We also wrote f of E as a function of E, and that we saw behaved like this. Fine. So this is how the two of them behave. Therefore the density of occupied states, so we will say n occupied subscript O, n occupied up to an energy level E, which is simply 2 times f of E d of E. That plot will look something like this. If assuming we draw it to the same scale, we can say this is EF, okay. So this is n occupied of E. So it will look like this, it will start off like this, it will go up to this, it will drop down to 0 and stay that way, okay. So in at 0 Kelvin, okay. So this is this picture has been drawn at 0 Kelvin. At 0 Kelvin, this is the picture we have of the probability of occupancy as given by the Fermi-Dirac statistical distribution. The probability of occupancy is as shown here. This function d of E gives us the density of allowed states. Okay, so density of allowed states is given by this function here. So that looks like this. Probability of occupancy looks like this. Therefore, at 0 Kelvin the density of occupied states looks like this. It is simply the product of these two by multiplied by a factor of 2, which you can ignore for the moment, but it is simply the product of these two. I mean we are not ignoring it, but in this plot, which is a schematic, we are not necessarily focusing on the constant 2, but you actually see that it goes up this way, it drops to 0 and goes at higher temperatures. The probability of occupancy changes, so we see a behavior that looks like this. So this is 0.5, you see a behavior that looks like this, right. So at a higher temperature, so this is at 0 Kelvin, so this is T0, this is T1 greater than T0. So we will say that this is at T0, at a higher temperature this distribution will look like this. Okay. So therefore we now have a picture which has now which is now a distinct step forward from where we were earlier. Previously we understood that we had to use quantum mechanical principles because our system was such, and therefore Maxwell-Boltzmann statistics was not good enough. We did Fermi-Dirac statistics, so we developed Fermi-Dirac statistics, and at that stage we basically found that this is the kind of behavior it has. So we recognized at that stage that when you raise the temperature of the system, only electrons very close to the Fermi energy are able to participate in the process. Okay, this EF is the Fermi energy. So only electrons very close to the Fermi energy are able to participate in the process. So therefore we recognize that as a concept that immediately indicated to us why it is that let us say the Drude model is incorrectly predicting the electronic contribution to specific heat, because according to the Drude model, which uses Maxwell-Boltzmann statistics, all electrons can gain energy as you raise the temperature, which means there is a huge number of electrons, they are all attempting to gain energy. So relatively speaking, that is a large amount of energy. In the Drude-Sommerfeld model, because it uses Fermi-Dirac statistics, only electrons very close to the Fermi energy are in a position to accept energy, and therefore it is a relatively smaller number of electrons that are able to accept that energy as you raise the temperature of the system, and therefore the prediction for the electronic contribution of specific heat distinctly decreases when you use the Drude-Sommerfeld model. And the reason of course that only electrons close to the Fermi energy can participate in the process is because all other states before it are occupied. Therefore an electron which is way below in energy level, if it attempts to gain the energy, it has to go to a valid site, a valid energy level rather, a valid energy level, and all those valid energy levels ahead of it are occupied or already occupied, because the probability of occupancy is 1. Therefore none of these electrons which are at lower energy levels can participate in the process when you use the Drude-Sommerfeld model, and therefore as a concept it is immediately clear how the Drude-Sommerfeld model handles the problem of electronic contribution to specific heat. But at the same time we recognize that this was not a complete picture, because it did not tell us what is the number of states that are available as a function of energy, and the exercise we have done today has enabled us to find that. We have looked at because we have accepted that there is confinement in the system, we recognize that the confinement led to quantization. Because it led to quantization, we realize that only specific values of the wave vector are allowed, which now correspond, which are based on the quantum numbers n. Okay, so those n values which are integer values permit only specific values of k in the system because of the confinement present in the system. Because only specific values of k are allowed, only specific values of energy are allowed corresponding to that. Okay. Now we also in today's class we said that okay, given this situation we understand that since there are relationships between E and k and E and n, you can plot this information in k space, you can plot this information in n space. Okay, and for our calculation purposes where one of the things we were looking for is to add more detail to this picture, and which is to find out the number of allowed state at each of these energy levels and therefore the density of allowed states, it is useful for us to start working with the n space. So therefore in that context we looked at this n space, we said that if you look at E versus n relationship you will get something like this, and in this system therefore all values of I mean all states which have the same value of energy lie on the surface of a sphere in n space. Okay, so that is the information that we put together, and in the n space, given that there is a sphere which contains all the states containing the same energy, if you divide it by the volume of a single state in n space, then you get the number of such states that are there present within that sphere. Okay, so up to a value n, all of this they are contained within that sphere. So whichever is your higher value of n energy, you take that energy, you will get a sphere. All the states within that sphere are energy values that are permitted corresponding to those n values that are permitted at those specific n values whenever they add up to it. And so when you divide by the volume of a single state, you get this as the number of this is number of allowed states. So please note that here also we are using an En, which is the number here. Okay, so this n of En is the number of allowed states, this is not the number of occupied states, this is simply the number of allowed states is this value here. Okay, so we find that that actually has this relationship of e power 3 by 2 with respect to energy. Then if we find that we noted that if you have a density of allowed states, the number of allowed states is simply the integral of the density of allowed states from 0 to En, and when you do that or rather if you differentiate now, you will get the density of allowed states. So we simply differentiated this expression here and we ended up with this expression here. Okay, and I said for example this a power 3 is the volume of the system that you are looking at. So now we have a density of occupied density of allowed states as a function of energy, we already and so we plotted that, and we have a probability of occupancy as a function of energy, so we are able to plot that as well. Okay, so given those two, we are now having the complete picture of the solid, which says as a function of energy what are the number of allowed states, okay, and also how many of them are occupied, all of that information is here, right. So this is actually the density of occupied states, okay, density of occupied states. So this includes both informations, how many states are there and to what extent are they occupied. Clearly at 0 Kelvin, given this kind of a picture, all the states up to a certain energy level, Fermi energy level, are fully occupied. Okay, so therefore it goes exactly up to that point, drops abruptly to 0 and stays at 0. Whereas at any higher temperature, as you approach the Fermi energy, there are there are states of energy value less than Fermi energy which are not fully occupied. Say for example this so some number of states are not getting occupied here, but some number of states at energy values higher than the Fermi energy are getting occupied, but this now contains the complete picture. So therefore the utility of this information is of course first of all that it is a more complete picture of the system, but the more immediate utility of the system is that whereas previously when we looked at the specific heat discussion, we could only descriptively say that you know the in the Fermi-Dirac in the Drude Sommerfeld model only energy values close to EF participate in the specific heat process in the process of gaining energy, and therefore that reduces the let us say the electronic contribution to specific heat significantly, but we were able to say that only descriptively. Given this information, where we actually have a much better feel for what is the complete system, what is the number of states and what is the probability that they are occupied, when since both those information is now held together in this picture, we can actually see that we can calculate now what is the we can put numbers down to this general idea that the Drude Sommerfeld model does a better job of predicting the specific heat. We can put the numbers down because we now have the background for it. We do not simply have probability of occupancy, we also have density of states, therefore we have density of occupancy. So with this we can say clearly what is the number of what is actually happening as you try to raise the temperature. You can get a much better idea of what is actually trying to happen as you try to raise the temperature. So what we will do is we will halt here for now. In the next class we will look at this particular problem and see what is the number we can put down for this process as you raise the temperature of the system, and how well now the model which has all the details, where we have arrived now we are still with the same Drude Sommerfeld model, but we have much more detail of that model incorporated into our equations. Having come this far, we will see how well we are able to actually predict this number of the electronic contribution to specific heat. Additionally, we will also see certain features related to the Fermi energy. Okay, so Fermi energy, so far I have sort of just stated that it is the highest energy level available in the system and we just put it down, but there are certain things we can say with respect to the Fermi energy, or certain ideas that we associate with the Fermi energy that we keep utilizing at various places. So we will at least spend a little bit of time in our next class looking at concepts associated with the Fermi energy, or different ways in which the Fermi energy information is conveyed in different discussions. So we will look at that in our next class. So we will do that, the Fermi energy discussion as well as the specific heat discussion, and see how everything that we have learned so far enables us to have a much better picture for what the solid is and how it is behaving. We still have some holes in the discussion, we still do not have complete detail of how something occurs in a solid, because there is even more detail that we can throw into the picture, and which we will do in classes after that. Okay, so for now we will halt, we will take it up in the next class. Thank you.